Good evening. Today I will be presenting on my research as seaweed as a carrier of microplastics as a part of my honors thesis defense. I very quickly wanted to begin by referencing some of the primary literature journals that contributed to my own research. Shim et al. Actually proposed the idea of using Nile red as a fluorescent dye for identifying and quantifying microplastics in solution, as read within the title. The main difference between their research and my own was the use of sand as the organic matter. They proposed an ideal concentration of 5 parts per million for the dye. However, I figured that since the dye was so expensive, I should continue looking into other concentration values, which led me to the second journal, which was written by Thomas Mays, in which a concentration of 1 part per million was proposed. I actually used this concentration throughout my research as well and found it to be just as effective. This was actually the journal that inspired my idea of using fluorescence spectroscopy for potentially identifying the concentration of microplastics in solution. This journal also proposed an ideal excitation wavelength range when identifying what a dyed microplastics should look like in solution. This range was between 450 to 510 nanometers, which I will reference later, but did allow me to identify and discriminate between what is a dyed microplastic and what is not. The procedure that I used in my own research was directly adapted by the third piece of literature with the exception of a few minor details. Very quickly, I would like to provide some background information on what a microplastic is. Microplastics are synthetic solid particles that range in size from about 1 micrometer to 5 millimeters in surface area. There are 2 different kinds of microplastics, either primary or secondary. A primary microplastic is found in nature or in a landfill, in the environment, exactly the way that the manufacturer had intended it to be. This is usually sourced from microfibers in clothing or even in small particulates within cosmetic products, such as face washes or actual makeup. Secondary microplastics are a result of environmental abrasions. They are worn down by environmental factors such as UV light, high temperatures, or, lucky for me, the motion of waves. The most prevalent forms of microplastics that I want to focus on in my research include polyethylene, polypropylene, and polystyrene, which are sourced by most plastic containers and everyday household items. However, there are other forms such as expanded polystyrene and extruded polystyrene, which typically come from insulation material or packaging material and are slightly less dense than the other 3 forms. So to provide you some sort of insight into the theory that led to my idea of using fluorescence spectroscopy, microplastics are selectively dyed by Nile red. Nile red has an affinity for synthetic polymers and should theoretically not dye any other organic matter that could potentially be suspended in solution. Therefore, fluorescence emission spectra should only be a reflection of the synthetic polymers. The fluorescence range provided to me by the second journal was an excitation range between 450 to 510 nanometers and an emission range of 580 to 640 nanometers, which again allows me to discriminate between a dyed microplastic with Nile red versus some other concomitant in the solution. The emission spectra of Nile red does change, however, based on the polarity of its environment. If there is any sort of interaction between the Nile red and whatever is in solution, this should theoretically be reflected in emission spectra. Lastly, seaweed has been proven to be a vector for microplastics. The idea of seaweed adsorbing microplastics is not an original idea. There have been previous studies that have proven this. What I aimed to do was merely quantify it. In the bottom right corner is actually the structure of Nile red. So several hypotheses for my own research were that fluorescence emission spectra could potentially demonstrate a direct relationship between microplastic concentration in a solution and emission intensity. For this, I had to consider various solvents, and the two that I used for my own research were acetone and methanol. Methanol was anticipated to have very little interaction with the plastics in solution, whereas I anticipated acetone to have an increased interaction either through degradation or potential dissolution. In the formation of my saturated samples, for the purposes of comparative data, I hypothesized that the seaweed would be able to absorb several plastics upon direct contact with a direct source of plastic. My methodology for every single seaweed sample that I used in my research was very similar. Initially, I started by putting approximately 25 inches squared of cut strips of seaweed in an oven for approximately 24 hours, allowing them to dry at 60 to 80 degrees Celsius. Upon the seaweed being dried, it was placed in a 1,000 milliliter beaker. Approximately 40 milliliters of 96% ethanol were added, and the mixture was agitated by hand for 15 to 20 minutes. Upon the mixture settling for a couple minutes, the supernatant was removed from the organic matter. Within the supernatant was also suspended particulates. For the supernatant to be removed from the solid particulates, it was allowed to evaporate out of solution. The solid particulates would then be placed into clean vials, and approximately 2 to 3 milliliters of a 1 part per million Nile red solution in either acetone or methanol would be added to each vial. The samples were then analyzed using fluorescence spectroscopy. I had several seaweed samples for my research. I initially began with store-bought samples that are termed as wakame and kombu. Their scientific names are shown on the screen as well. I had two samples in particular that I had identified to be overly saturated, since the solutions actually resulted in crystal formation over time. These samples are referenced throughout my research as having been made in May of 2019 and in June of 2019. These were more of a testing kind of sample for my research. The sample made in May was prepared from kombu, which was a prepackaged and previously dried seaweed. And the sample prepared in June was actually agitated with a plastic bag in the solution. However, they both led to crystal formation upon the supernatant being allowed to evaporate and the particulates simply sitting in a beaker over time. I also was provided with samples from St. Kitts and Nevis. Specifically, I was provided with 4 different species of seaweed. The way that these seaweed samples were prepared is they were each individually dried, and the mass was taken of each individual species. The species were then cut to obtain approximately 4 different samples of each species with approximately the same masses. The general procedure was then applied to each seaweed species. I also made a range of polyethylene terephthalate standards, which actually came from store-bought glitter, and a few high-density polyethylene standards that were sourced from a milk jug. This is just an example on the left of what my samples ultimately looked like. I eventually adapted an organization system in which I use blue tape to represent a methanol as the solvent and pink tape to represent acetone as the solvent. As you can see, I tried to keep a very similar size range for the vials, and the dark amber actually helps in reducing the effect of UV light degrading the fluorescence of the sample over time. The reason that I chose fluorescence spectroscopy is actually because I'm very fascinated by the instrumentation. The instrumentation in regards to the excitation source and the actual sample signal detector has an arrangement of 90 degrees. This means that there's no interference whatsoever by the actual excitation source, and this 90-degree angle demonstrates a more complete profile of the fluorescence of the actual sample. I created a few what I like to call saturated samples in order to test the adsorption capacity of the seaweed. This would allow me to speak in terms of relativity when I moved on to my environmentally obtained samples from St. Kitts. I initially started with by placing the same area of seaweed in a filled water bottle, a half empty water bottle, and a completely empty bottle. In the completely empty bottle, I allowed it to lay laterally with the seaweed making direct contact with the plastic in order to see if it could absorb it without any water interface. The half-filled empty bottle was just to provide an air interface as well, and the filled water bottle was to see how the seaweed would potentially absorb microplastics while being fully submerged. This is several emission spectra from the store-bought samples. The particulates were suspended in acetone and Nile red, and they provided the following emission spectra. As you can see by the spectra in figure 7 and figure 8, there was some sort of a peak separation that occurred. I have personally identified the peak splitting to have been a potential source of the overly saturated sample. However, interestingly enough, the maximum wavelengths at which these peaks are centered actually average out to be a relatively accepted wavelength value for the particular solvent system. So for example, in figure 7, a peak at 580 and a peak at approximately 680 will average to be about 630, which is exactly the emission wavelength range that a sample such as this should be fluorescing in. This could also potentially be due to the fluorophore or Nile red itself. Various energy states could be excited upon the light source hitting it. This is directly reflected within the emission spectra as well. However, in figure 6, you do notice that a much lower intensity could potentially have some sort of reflection with the concentration of microplastics in the sample. So for future studies, I considered reducing the concentration of particulates in a sample extensively. I also wanted to very quickly cover the results from the packaged and previously dried seaweed, since I did have crystals eventually form. The excitation spectrum actually shows activity in the range that I had mentioned earlier, between 450 to 510 nanometers. There's various peaks in this range that actually detract from the smooth curve that is normally expected in fluorescence. This leads me to believe that there's potential activity here from concomitants or from microplastics in solution. Again, for a fact, this solution was overly saturated with particulates in a solution and also resulted in a very similar peak splitting, just to further support the idea that this is potentially due to saturation. In figure 9, you will see what my crystal structures actually resulted as. Just to provide some sort of a qualitative comparison, I found an image of an atomic force spectroscopy photo of a polyethylene crystal. The literature actually describes a sort of rectangular growth in which the length and width grow in different magnitudes, which was also exemplified by my own crystal structures. Uh, Again, both of my samples made in May and in June, which I intended it to be overly saturated, resulted in crystal formation. So I decided to collect some infrared data. The infrared data shown in figure 11 and figure 12 is relatively similar in similar areas. For example, between 3200 to 3300, there is a rounded peak. This could potentially be due to influence of carbon dioxide from the organic matter in solution or leftover remnants of the alcohol solvent. There is a sharp peak